Hello, my name is William Estes, and I'm a middle and high school science teacher, but these days I've been doing mostly remote teaching because of the coronavirus and because of the quarantine. So I just wanted to give you a look at how I do remote teaching and kind of give you an idea of my studio setup. So first thing is first, I've got this bizarre aquarium thing going on here. Let me get this set up. So this is how I do my physics lessons most of the time. The point is to kind of recreate what I've got in the classroom. And one of the main tools that I've got in the classroom is a big whiteboard. So in order to be able to write, almost like Khan Academy style, I've come up with this. Let me just set this up. So of all the uber professional equipment here, I'm using a white plastic grocery bag as a diffuser. Let me get the other side on here. Now, there we go. So that's nice and well lit under here. I finished finessing this today. I've got this like duct tape frame so I can hold a piece of paper in place. And this way, the video that's facing underneath should be completely washed out in terms of just, the background, which is white. But anything that I write on here should show up in pretty high contrast. So you got like an overhead view there. You should be able to see what I'm doing in this camera. And this down here is going to be the result that my students get. So here's what I've got so far. Today is Tuesday. It's Tuesday night, so I'm making a lesson that I've got to post tonight, so it's ready Wednesday morning. And so in physics right now, we just finished up doing heat transfer, heat capacity, thermal conductivity, and before we went into this, I was trying to build towards a kind of thermodynamics unit, but the problems kind of were so complicated that I had in mind that without me being present in the classroom, I kind of don't want to push it as far as I went before. So I just kind of derailed that unit. I'm making it end on a whimper before I can move on to something else. I gave them a sample problem and a homework problem that was based on a hot air balloon. What I need to do right now is make a solution video. So what I'm going to do is I'm going to go over the problem that I gave them. Then I'm going to work out the solution as if I were going over it on the board. And I've got another problem to go over with them. So I just have to make sure I've got enough paper here that I can quick grab them when it's time. I had to work the problem out all, ahead of time so that I wouldn't bumble around. Wouldn't bumble around on it. Oh, is that? You know what? I think I might need to. There we go. Oh, it's a good thing I did that. Yeah, I need to change that exposure. Okay. Right. So, first video. Okay. Hey physics class, so today I'm just going to be going over the last couple of problems that I've given to you. It's going to take long enough that it's going to be a whole day's work anyway, so I'm not going to add on to any of that. So the first thing that I want to do is to give you the solution to the hot air balloon problem. So let me go ahead and get a drawing for perspective. I really hope this is the last time I have to draw a hot air balloon. I never thought I would draw so many hot air balloons, but life throws you curveballs, and you just got to learn to deal. Float along. So the balloon that I gave you in the problem had these specifications. So the mass of the material in the balloon itself, the basket and the fabric and all that, was 500 kilograms. The volume of the material, remember the deflated volume just of the basket and the fabric in the balloon itself, that had a volume of 10 cubic meters. Now, I want to make sure that I don't mix these up with the mass and the volume of the air. So I'm going to stick a little b here as a subscript. So that's the mass of the balloon. This will be the volume of the balloon. Later on, I'll refer to it of the air. So that'll be a subscript of A. Anyway, so we've got a mass of 500 kilograms, a volume of 10 cubic meters. Now, the volume of the air inside, that was much larger. The volume of the air was going to be 2,000 cubic meters. Can you read that? That's yeah, you can read that. All right, so that's 2,000 cubic meters. Okay, so that right there is just the data on the balloon. And if you remember, the point of the problem was we need to heat up the air so that it expands, some air molecules leave, and the density goes down to match the density of the air. So if you will recall, the density of air is equal to 1.225 kilograms per cubic meter. The idea is we need to get the density of this balloon to equal that. In other words, this quantity, 1.225, must be equal to the total mass of the balloon plus the total mass of the air contained within the inflated balloon over the volume of the balloon itself plus the volume of the air within the balloon. Density is always mass divided by volume. Since we're talking about the density of the combined balloon and air it contains, that's why I've got the sum of the masses in the numerator and the sum of the volumes in the denominator. So let's just fill in the values that we know, see what we don't know, and we'll just have to solve for them. So the mass of the balloon we know, 500 kilograms. The mass of the air inside, though, that's actually what we don't know. So we got the mass of the balloon, it's 500. Mass of the air, that's unknown. What about the volume of the balloon? Well, that's 10. And the volume of the air, that's 2,000. Please remember, the whole point of choosing a particular thing is so that it will behave, its pressure and its volume are going to change based on the physical properties of this thing. I chose a balloon so the volume would remain constant and the pressure would remain constant, and only the temperature and the amount of air inside can vary. So we've got the density of an inflated balloon. We know that it must equal this density, but before I throw that in there, let me simplify this real quick. Since I've gotten rid of MB, I'm gonna I'm gonna keep the MA because I don't want that to get lost. So this simplifies to 500 plus the mass of the air inside over 2,000 plus 10. Okay, so this is an expression for the density of the inflated balloon, and we just need to get its density to equal that amount. So we're trying to solve for the mass of the air inside. So the first most obvious thing that we need to do is we need to multiply both sides by 2010. If we do that, we're going to end up with 500 plus MA equals 2,462.25. Okay, we're almost there. To get this by itself, we need to subtract 500 from both sides. And so that means in order for this balloon to float, to be weightless, it's going to need to have a maximum mass of 1,962.25 kilograms of air on the inside. Okay, so just so we are clear, in order for this balloon to be as light as the air, there can only be 1,962.25 kilograms of air in this 2,000 cubic meters. All right? Well, in order to make that happen, we're going to need to take into account the density of air. If you look back on the previous video, we did end up finding the molar density of air. So for this case, we're going to be taking the density of air to be 0.0274 kilograms per mole. That was the number that we used in the last video. So if this is our density, and we know that the mass of air we're going to have is 1,962.25 kilograms, well then, in order to figure out how many moles of air we can fit in this balloon, we just need to divide this mass by that density. So let me write this out so you can see the units cancel. 1962.25 kilograms over 0.0274 kilograms per mole. You got your kilograms canceling. You've got 1 over moles. That's going to come up in the numerator. And so 1962.25 divided by 0.0274 is equal to an enormous number, 71,614.96 moles. Now, that number might seem huge, but if you remember from the last problem, we had in the 30,000s and in the 40,000s. So it's an awful lot of moles of air. That's not unreasonable. Okay, so that's how many moles of air in an inflated floating balloon. Wait, I'm sorry. Hold on a second. Yeah, that's right. In an inflated hold on a second. I think I screwed up. Hold on a second. Oh, doggone it. Did I get that right? I've got so many numbers, I think I mixed them up. Okay. So here's the thought that just panicked in my head. I thought I just used the density of air at STP, like at 0 degrees, but I just found the quantity of air that will be in it when it is not at STP. And I panicked that I used the wrong number, but I forgot I'm using the molar mass. This has nothing to do with its temperature. So obviously at this point in the video, I'm going to have to pause it and edit it, but it should come out smoothly. All right, so yeah, okay. In an inflated floating balloon. Let me back up a second, make sure I can run into this. I hate having to edit these videos. It takes forever. All right, so where am I? Got it. Okay. Let me get a better view there because I want you to see. Maybe. I don't know if that helps. Okay. Where am I now? All right. All right. I need to get my bearings. See, this is so much easier to play off in a classroom because generally speaking, there's like at least a couple students who are following along and can help me get back onto it. Let me see, where am I? Yeah, okay. Okay, at this point, we're ready to use the ideal gas law. So what I'm going to do is I have to set it up twice. Once is when it's not inflated, and I'm sorry, once is when the temp. I barely got into it. I can just start up again. Okay. All right, we're ready to use the ideal gas law now. We have to do it twice though. Once is going to be before it got heated up. So this is going to be our still on the ground before the heat is on, inflated but not floating. But then we have to do it again where it is inflated and floating. And if you remember from the last problem, it works out like this. If the pressure is always 1 atmosphere and the volume is always 2,000 cubic meters, it's going to be the same before and after. Well, if this is the same before and after, then that means this will be the same before and after. Okay? The only part of the problem that we need to really worry about is nRT. Now, if I needed to do a change, from beginning to end, that would be fine. But it turns out, because they stay the same, I can just do one of them and it will stand in for them both. Man, that was really idiotic and confusing. So I'm just going to edit that whole thing out because I kind of contradicted myself. Ugh. This is not an ideal way to teach. All right, so okay, right. Okay, so the temp. All right, so the question is, what temperature will have 71,614.96 moles of air have a volume of 2,000 cubic meters at 1 atmosphere of pressure. This is the situation that is described by our problem. Remember, I've got a balloon with a volume of air of 2,000 cubic meters. When the balloon has the same density as the air, that means that there's 1,962.25 kilograms of air in there, which turns out to be only 71,614.96 moles. So I've just got to set up the ideal gas law for these values and solve it. PV equals nRT. So a word about this. The volume is in liters. This volume is in cubic meters. There are 1,000 liters in 1 cubic meter. And that means that 2,000 cubic meters is actually 2 million liters. So that's the number I'm going to have to use. Okay, so let's fill this in. We know what the pressure is. The pressure is 1 atmosphere. The volume is going to be 2 million liters. I'm going to put that like this so it doesn't run off the frame. So this is PV equals, oh, I might run off the frame as it is. Let me see if I can stay in it. So 71,614.96 moles. N. R is the same number as it was in the previous problems, and that is 0.08206. That's units liter atmospheres per mole Kelvin. All right, I just barely have enough room for the temperature. But the temperature is what we don't know anyway, so hooray, I'm safe. That temperature is going to be in kelvins. Okay, so solving for this temperature is just going to be a big fat calculator bomb. It's going to be 1 atmosphere times 2 million liters over 71,614.96 moles times, sorry, that should be times, it looks like a minus, times, there we go, 0.08206. Okay, calculator does this, you end up getting an answer of 340.3. 340.3 kelvins. Subtract 273, you get 67.3 degrees Celsius, which is a nice and toasty 153 degrees Fahrenheit. Okay, so to summarize, that's how much air you can have in the balloon so that, you know what, this whole thing is dumb. I'm just going to cut it off right after that. Oh, right. So I'm going to edit it right there. So that's several major edits in this physics video so far. Okay, so I do have another problem to go over. This is all the fun. Okay. Okay, there was one more problem. This is the one that I gave you yesterday. It had to do with canning. Right, so you've got yourself a jar. I'm going to draw a very basic jar, sorry. I spent all my artistic... That is a sorry looking jar. All right, so we've got a jar. The air on the inside has a temperature of 373 kelvins. That's just boiling. So basically you've got a empty jar that just came out of boiling water. So the air inside is at the same temperature as boiling water. Just say it's steam or whatever. And the volume of this jar is 500 milliliters or 0.500 liters. So we put a lid on it. The art just makes no sense. We just accept this. And then it cools down. I can't believe I have to copy this awful drawing now. It looks like mayonnaise. I have no idea. Anyway, enough art criticizing. After this cools down to room temperature, it's now 293 kelvins, still 0.500 liters. The question is, if this started out with a pressure at 1 atmosphere, what's the pressure now? So if we were to put this in the context of the ideal gas law, we've got a before, which is 1 atmosphere. The volume is 0.5 liters. Now, I'm actually not going to bother calculating the number of moles in there, and you'll see why I don't need to later. So the number of moles in there is just the number of, yeah, that's totally an N. The number of moles is just the number of moles. The ideal gas constant is what it is. And the temperature before is 373. So here's one of the reasons why I don't actually need to calculate the number of moles in there. So this is before. This is going to be a container whose volume can't change, and also the number of moles inside can't change. So I've got a PV equals nRT for before, but now I've got to have a PV equals nRT for afterwards. What are all the things that are the same? The volume stays the same. It's a jar. It's not going to flex. So the volume is still 0.5 liters. None of the gas has escaped. So N is still the same. This is a constant. It's still the same. There's only two things that have changed. And they are directly proportional because they're on opposite sides of this equation. This temperature has changed to 293, which means that this pressure must also have changed proportionally. So think about this like if you were doing algebra, whatever you do to the right side, you must also do to the left side. In order to get from 373 to 293, what you can do is multiply by the fraction 293 over 373. These two lines are algebraically equivalent. And because the temperature and the pressure are the only things that are changing, and they are directly proportional, you just multiply both sides by 293 over 373, and that's what you get. So this is clearly a fraction. The pressure inside is going to go down, and this simplifies to approximately 0.786 atmospheres. Okay, so that's the answer, but real quick, what does that mean? What does that mean? So if you don't know, atmospheric pressure of 1 atmosphere is approximately 14 pounds per square inch. Okay, so what that means is take something that's about a square inch. There's enough air pressure on that to exert 14 pounds of force on it. So if you've got a lid like this, I pulled a lid out of my pantry just to measure it, and I measured it to be about 12 square inches. So what that means is there is 12 times 14 pounds of air pressure on a lid like that, which is like it's about 175 pounds. Okay, so you probably know someone who weighs that much. Them standing on that jar lid, that's how much force the air is putting on it. Why doesn't the jar collapse? Well, because there's air inside also. So there's 175 pounds pressing down from the top, but there's also 175 pounds pushing up from underneath until it cools down. Now I've got 175 pounds pushing down, but only 78.6% of that pushing back up. Okay, so what that means is the equilibrium is off by almost a quarter. So that basically means that at the end, there's a net force in of about 40 pounds. So, how difficult would it be to open this jar? It would be as difficult as lifting that lid if it had 40 pounds sitting on it. Anyway, between this and the last problem, that was a lot. So, I'm not going to add anything else to that. I'll just, I'll have something else for you tomorrow. All right. See ya. Oh my goodness gracious, that was exhausting. Oh. So before we went remote, I had this conversation with my students. I told them that teaching was a lot like, oh, here, I can stop that. I told them that teaching was a lot like stand-up comedy because the way that I go forward has to do with the responses that I'm getting. You know, I kind of have to feel the room. So I described it kind of like, so I'll say something. It's like, huh? And and then they give me a response of like, yeah, or no. And I have to make my next move based on how they're responding to what I'm doing. Making a pseudo lecture like this, it's it's a very bizarre experience. Anyway, so I've got to put that away because I've got one more class to do before I can start editing and call it a night in terms of making stuff. So I need to get this out of the way because I have something else now. I'm gonna keep the audio going and get this out of the way. So that was physics. Now I've got to do something for earth science. Excuse me, aquarium. Out of here. Ugh. Oh. Right. So for this one, I actually need the other computer here. Oh, please don't tell me you stopped. Oh, good. It was still recording. All right. Anyway, so I need to use you now. Sorry. Okay. So I'm going to do something on this screen, and I'm going to be recording the screen, so you'll be able to see that. I just need to save this. Okay. Wow, that was more than half an hour. When I edit that, it's probably going to be like 25 minutes. Watching someone do math for 25 minutes. That can't be that fun. All right, so get out of that. So new screen recording. And there we go. So I got a screen recording now. And I've got a couple things ready here. Okay, so what we have been doing is rivers in earth science. We were doing, stream channel, stream erosion, deposition, all that stuff. And once again, my plans have been derailed by the quarantine, and I need a way to transition to the next topic without being able to do like the traditional review, test everything. Because I don't know if this occurred to you, but like tests are really hard to do remotely. It's pretty much impossible to guarantee that there's no cheating. You basically have to make a cheat-proof test, which It's basically just an open note essay, which is a lot harder to do in science than it is in other subjects. But anyway, don't need to figure out the whole curriculum right now. I just want to show you what this is and how it works. So I've got, you know what? I don't need to explain it to you because I'm making the tutorial. So just watch the thing. Okay. Right. Are we still... Okay, good. Hello, Earth Science. We've got something else to do with rivers here. Hopefully you found the links that I put on the LMS. There's one link that takes you to a site that finds the elevation. And the other is, of course, just Google Maps. So first thing that you're going to want to do is find the mouth of the Susquehanna River on both those maps. So just in case you got a little navigation problem with that, you can watch me go in. I'm going in. There's Pennsylvania. There's Maryland. Here is the Chesapeake Bay. Zoom in on that. Hey, there's Havre de Grace. And there, that's the mouth of the river right there. Let me just get in a little closer. I don't need all those menus on the side. Okay, so this is the elevation map right here. Let me go over to Google Maps. Hey, we're back out in space, so let's zoom in here. So there's Pennsylvania. There's Maryland. Let me go down to the Chesapeake Bay. I should be seeing Havre. Yeah, there's Havre de Grace again. And here is that. So even though these two maps look a little different, you should be able to recognize it. So just get a couple landmarks to get your bearings. Here's one bridge, another bridge close to it. This even says the highways. This is Route 40. That's I-95. And if you go up here a little bit, past these islands, there's another one up here, and that's Route 1. Let me just make sure I'm looking at the same thing over here. Yep, see? I've got a bridge down here, a bridge up here. This doesn't say what the highways are, but you should be able to recognize the shapes. Up here, past an island, and there's another road. So the information that you're going to be looking for is going to be a combination between these two maps, and I'm going to show you how to record it. So here's the first thing. I want to go from the mouth of the river all the way up in a straight line to this road. And I want to measure the distance. Here's how you measure the distance on Google Maps. If you're on a PC, you can right click. I'm using a MacBook, so I have to do control click. But you can measure a distance. So if I measure a distance from there, I just need to go find the next point. And I'm going to go all the way to that road. So can you see how far that is? That is 9.1 miles from the mouth of the river to that bridge. All right, now I'm going to go to those same places on this map. Oops, there we go. Mouth of the river. Okay, surprise, surprise. The Chesapeake Bay is at sea level. I mean, did that honestly surprise anybody? It's part of the ocean. It's just a little part of the ocean that's like, you know, stuck between two different parts of Maryland, but it's at sea level. But the entire river is not at sea level. So when I go up here and click on that, would you look at that? That is 26.2 feet above sea level. So between these two maps, I have that 9.1 miles away from the mouth of the river you go up from 0 feet above sea level to 26.2 feet above sea level. Okay, how am I going to record this? So I'm going to open up a table, and I just need 2 columns. One column is going to be a distance. The other column is going to be a height. So let's start out. If I am 0 miles away from the mouth of the river, I had a height of 0 feet above sea level. Okay, you don't need to write this explanation. This is for your benefit. So 0 miles from mouth of river, 0 feet above sea level. Isn't it fun listening to someone read what they're writing? Anyway, let's go back. So I'm still measuring distances here. So I need another landmark. I'm going to go up to the Pennsylvania-Maryland line because that's kind of another straight line. Now you'll notice how it's counting distance. It's the sum total now, 14.47 miles. This is almost 14 and a half miles from the mouth of the river. How high is it there? If I go to the Pennsylvania-Maryland border and find the height, I'm all the way up at 105 feet. So those numbers again are 14.47 miles. Let me write that down. 14.47 miles and a height of 105 feet. Again, that is 14.47 miles from mouth of river, 105 feet above sea level. Now, even though this number is a lot larger than that one, remember that this is miles and that is feet. 105 feet is goodness, what is it? 105 divided by 5,280. Yeah, it's like 2% of a mile. So, yeah, this is very, very gradual, which of course it is. Otherwise, it would be a waterfall. So what you need to do is you need to trace a path up this river, getting distances. There's 20.27 miles. And it is right next to these islands. Hopefully I'll be able to see them in the other map, but just in case I can't, it's right underneath this park, which is right underneath that lake. Oh, there it is. See? There's the lake. There's the park. There's the spot. Now, this is really important. These islands are above the river. So I want to make sure that I'm picking spots out in the middle of the water. 98.4 feet. Something else to keep in mind. So these are not very precise. We would get better numbers if we were using Google Earth. This water should not be going uphill. So yeah, if you see that, don't let it freak you out. It'll work itself out later. So, oh, I'm sorry. I already forgot the number. 98.4. So how far do I want you to go with this? Well, if I go back to this map, if you went all the way up to where we are, you'd have to go up to this bend. Because here's 462, here's Route 30, York's right over there. So this would be up far enough. If you got all the way up to Route 30 to that bend, so like your final point could be right in the middle of that bend, well, that's not going to work because I missed a lot of the twists and turns. You're going to have to follow the curve a bit more closely and do the same thing with this altitude. Make sure you're sticking it right in the middle of the water. You should be able to get a table. You might have 10 numbers in there. That would be enough. Just imagine how awful this would be if you had to do the whole 444 miles of the river. Oh my goodness. No, 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 no. So let me get this out of here. Doing graphs in Google Sheets is a skill in and of itself. If you know how to do this, that's great. But if you just have the numbers, that's okay. One of the things that you can do with this is make a graph of it. That would be this picture right here, insert chart. And in this particular case, yeah, it's a pretty messed up view. There we go. So this is extremely scrunched up and only a couple points, but that's what's called the stream profile. It shows the change in height of the river over distance. Anyway, get out of here, you graph. Right, so what I want you to do is between this map and this map, collect increasing distances, and hopefully they're increasing heights. See if you can get 10 numbers. And if you feel comfortable with it, go ahead and graph it. Again, that's a skill in and of itself. I won't hold it against you if you don't. Anyway, if you have any questions, feel free to email me. But other than that, good luck. Oh. So, well, save Earth Psi river profile. Okay. So, what have I got here? I did the solutions to 2 physics problems for half an hour. Then I demonstrated an earth science thing, computer activity. It's almost a digital lab. That took 13 minutes. So between setting this up and actually getting it done, I think I've been doing this for about an hour. And I haven't made a deal of this yet, but so my kids are out of school, of course. They're being homeschooled. And this is when I get this stuff done. So remote teaching is not just an alternate form of teaching. It's a completely different work schedule. I could set aside school day hours 8 to 3 or whatever, but that's just not compatible with the rest of what's going on at home. So I got some editing to do, and oh my gosh, I'm so tired.